Next topic is symmetric groups. First, what is a permutation? Let A be a set. A permutation on a set A is a function f mapping from A to A such that f is 1 1 and onto. Next, permutation group. The set of all permutations on a set A under function composition forms a group called the permutation group. Means set of all the permutations on a set A under function composition. This forms a group under the permutation group. Means here binary operation is composition function. The permutation group on the set A is equals to 1, 2, 3, so on till n. For n belongs to natural numbers is called the symmetric group and is denoted by Sn. Now we define the symmetric group S3. Set A is equals to 1, 2, 3. Now possible permutations on set A are, means it should be both 1, 1 and onto. One, two, three, 1, 2, 3. One possibility is 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. Second possibility is 1 is mapped to 1, 2 is mapped to 3 and 3 is mapped to 2. Third possibility 1, 2, 3, 1, 2, 3. 1 is mapped to 3, 3 is mapped to 1 and 2 is mapped to 2. Fourth possibility 1, 2, 3, 1, 2, 3. 1 is mapped to 2, 2 is mapped to 1 and 3 is mapped to 3. Fifth possibility, 1 is mapped to 2, 2 is mapped to 3 and 3 is mapped to 1. Sixth possibility, 1 is mapped to 3, 2 is mapped to 1 and 3 is mapped to 2. So only these 6 possibilities are possible for this set A equal to 1, 2, 3. So order of S3 is 6. Now I can write this in array form also. So these are 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. Next one, 1, 2, 3. 1 is mapped to 1, 2 is mapped to 3, 3 is mapped to 2. Third one, 1 is mapped to 3, 2 is mapped to 2, 3 is mapped to 1. Fourth, 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 3. 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. 1 is mapped to 3, 2 is mapped to 1, 3 is mapped to 2. Is this clear?
Yes, ma'am.
And in cyclic notation, one is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. This is identity. Next, this is 2, 3. This is 1, 3. This is 1, 2. This is 1, 2, 3 and this is 1, 3, 2. So S3 contains identity 2, 3, 1, 3, 1, 2, 1, 2, 3, 1, 3, 2. Next, we will learn how to multiply two permutations. Multiplication of two permutations. One, two, three, 1, 3, 2, 1, 2, 3, 3, 2, 1. So I will start from the right side. Here 1 is mapped to 3 and 3 is mapped to 2. So finally 1 will be mapped to 2. 2 is mapped to 2, 2 is mapped to 3. 3 is mapped to 1 and 1 is mapped to 1. So this is basically 2, 3 and this is 1, 3. Their product is 1, 2, 3. And I want to check whether this is abelian or not. So 1, 3 into 2, 3. This is simple. Firstly, I will write 1. Here 1 is mapped to 1 because 1 is not present now. So 1 is mapped to 1 and here 1 is mapped to 3. Here 3 is mapped to 2 and 2 is mapped to 2. So clearly 2 3 into 1 3 is not equal to 1 3 into 2 3. So S3 is a non-abelian group. This implies Sn is a non-abelian group for all n greater than equal to 3. Now some properties of symmetric group. Order of Sn is n factorial for all n greater than equal to 2. Second, every permutation of a finite set can be written as a cycle or as a product of disjoint cycles. For example, 1 2 3 4 5. This is written as a cycle, and 1 2 3 into 4 5 6. This is written as a product of disjoint cycles. Next, disjoint cycle commutes. Next, how to find order of a permutation. A cycle of length n has order n. For example, if I have this cycle 1 2, then cycle is of length 2. Therefore, order of this cycle is 2. And how it has been calculated? 1 2 into 1 2. This is order na? I am multiplying this element with this element only, same element, to get identity. So this will be 1. 1 is mapped to 2. Here 2 is mapped to 1. 2. 2 is mapped to 1 and 1 is mapped to 2. 3. Here 3 is mapped to 3. Here also 3 is mapped to 3. So this is identity. Next, 1 2 3. This is cycle of length 3. Therefore, order of 1 2 3 is 3. How we have calculated this? 1 2 3 into 1 2 3. This will be 1. 1 goes to 2. Here 2 goes to 1. 2 goes to 3. 3 goes to... एक second. 1 2 3 1 2 3. 1 goes to 2. 2 goes to 3. 3 goes to 1. 1 goes to 2. I am not getting identity element. I will multiply this again. 1 2 3 into 1 3 2. So 1 goes to 3. 3 goes to 1. 2 goes to 1. 1 goes to 2. 3 goes to 2. 2 goes to 3. Now this is identity. Next, the order of a permutation of a finite set written in a disjoint cycle form is the LCM of the lengths of the cycles. The order of a permutation of a finite set which is written in a disjoint cycle form is the LCM of length of the cycles. For example, 1, 2, 3, 3, 5, 6, 8. 1, 2, 3 is a cycle of 3 length, so order is 3. 3, 5, 6, 8. This is a 4 cycle, so its order is 4. Both are disjoint cycles. So order of 1, 2, 3, 3, 5, 6, 8. This is LCM of this cycle's order 3 and this 4. So 12. Next, if I have 1, 2, 3, 4, 5, 6, 2, 1, 5, 4, 6, 3. I have given this in array form. Find the order. Firstly, write this in cyclic form and then find its order. Find it.
Six.
Yes. What is the cyclic form for this?
1, 2,
Hmm.
then 3, 5, 6, then 4.
Okay. So order of 1, 2, 3, 5, 6 is LCM of 2 and 3, which is 6. Next, every permutation in Sn n is greater than 1 can be written as a product of two cycles. For example, 1, 2, 3, 4, 5, 6. This can be written as 1, 6, 1, 5, 1, 4, 1, 3, 1, 2. Simply, I have written like this: 1, 6, then 1, 5, then 1, 4, 1, 3, 1, 2. Next example, 1, 2, 3, 5, 6. This is already in 2 cycle. Then 3, 6, 3, 5. 1, 2, 3, 3, 5, 6, 8. So 1, 3, 1, 2, 3, 8, 3, 6, 3, 5. Next, the decomposition of a permutation in Sn in 2 cycles is not unique. For example, 1, 2, 3, 4, 5. This can be written as 1, 5, 1, 4, 1, 3, 1, 2. This can be also written as 4, 5, 5, 3, 2, 5, 1, 5. Next, what do you understand by even permutation? A permutation that can be expressed as a product of even numbers of two cycles is an even permutation. For example, एक second. One, 3, 2. This can be written as 1, 2, 1, 3. Even number of two cycles. Therefore, it is an even permutation. Note, if the length of the cycle is odd, then the permutation is an even permutation. For example, 1, 2, 3, 4, 5. This is odd length cycle. This can be written as 1, 5, 1, 4, 1, 3, 1, 2. So it has even number of two cycles, so it is an even permutation. Next, odd permutation. A permutation that can be expressed as a product of odd numbers or two cycles is an odd permutation. For example, 1, 2, 3, 4. This can be written as 1, 4, 1, 3, 1, 2. So it has product of odd number of two cycles. There are three two cycles. So this is an odd permutation. Next, product of even permutations is even. Product of two even permutations is even. Product of two odd permutations is also even. Product of an even and an odd permutation is odd. Next theorem. The set of even permutations in Sn forms a subgroup of Sn called the alternating group of order n factorial by 2 and is denoted by an. More properties of Sn. First, if H is a subgroup of Sn, then either every member of H is even or exactly half of the members of H is even. Means if H is a subgroup of Sn, then either every member of H is even or exactly half of the members of H is even. Second, the inverse of a cycle is just the digits in reverse order. For example, if I have this cycle A1, A2, so on till An inverse, then it will be written as An minus 1, An minus 2, so on till A2, A1. For example, inverse of 1, 2, 3. This will be 3, 2, 1. Inverse of 1, 4, 7, 8, 9, 6. This will be 6, 9, 8, 7, 4, 1. Therefore, if alpha is an even permutation, then alpha inverse is also an even permutation. And if alpha is an odd permutation, then alpha inverse is also an odd permutation. Next, center of Sn is identity. Dn, dihedral group, can be viewed as a subgroup of Sn Similarly, Zn can also be viewed as a subgroup of Sn. Next, number of elements of a particular order in Sn. How to find number of elements of particular order in Sn? So possible orders, if I discuss in S5, it can be 1, 2, 3, 4, 5, 6. So S5 has 5 elements, 1, 2, 3, 4, 5. So 1 cycle is possible, 2 cycle, 3 cycle, 4 cycle, 5 cycle is possible, 6 cycle is possible by considering 1, 2, 3, 4, 5. Their LCM will be 6. So order 1, this will be identity element. Now without writing this S5 group, I want to know that how many elements of order 2 are there, because in total order of S5 is 5 factorial. So it will have 5 factorial elements. So order 2 element, this can be like this: 1, 2, 3, 4, 5. This is order 2. So formula is 5 factorial upon this cycle. This is a cycle of length 2 and it is present one time only, so 2 to the power 1. Next, into 1 factorial into how many 1 cycle are present? 3. So 1 to the power 3 into 3 factorial. So 5 into 4 into 3 factorial upon 2 into 3 factorial. So 10. And one more type of 2 cycle are possible: 1, 2, 3, 4, 5. By taking this LCM of 2 and 2, I am getting order 2. So this will be 5 factorial upon 2 to the power 2, because there are 2 cycles of length 2 into 2 factorial into 1 to the power 1 into 1 factorial. So this will be 5 into 4 into 3 into 2 factorial upon 4 into 2 factorial. So 15. So in total order 2 will be 10 plus 15, 25. Is this clear? Any doubt?
ये क्लियर नहीं हुआ मुझे. 1 2 की पावर 2 स्क्वायर 2 साइकिल है ना ये. 2 स्क्वायर इंटू 2 फैक्टोरियल एक में ही करेंगे, बाकी में तो 2 स्क्वायर इंटू 2 नहीं करेंगे.
मैं फॉर्मूला बताती हूँ, एक मिनट. if sigma is equals to sigma 1 to the power n1, sigma 2 to the power n2, so on till sigma k to the power nk, where sigma I is permutations of length Li repeating Ni times then number of such sigma in Sn is equals to n factorial upon L1 to the power n1, L2 to the power n2, so on till Lk to the power nk into n1 factorial, n2 factorial, so on till nk factorial. So sigma I is a permutation of length Li repeating Ni times. So 1 2 is a permutation. It is of length 2 and repeating only one time. So that's why I have taken 2 to the power 1 into 1 factorial. Next, there are 3 cycles of length 1. So 1 to the power 3 into 3 factorial. And here there are 2 cycles of length
Yes, ma'am.
2 which
Now
are
clear.
repeating 2 times.
Hmm.
So 2 square into 2 factorial. Now is it clear?
Yes, ma'am.
ठीक है. Next, the symmetric groups are rich in subgroups. Here we will see subgroups of S3. S3 is equals to identity 1 2 1 3 2 3 1 2 3 1 3 2. So H1, this is identity. H2, this is identity comma 1 2. H3 can be identity comma 1 3. H4 identity comma 2 3. H5 identity comma 1 2 3 1 3 2. And H6 complete S3. So S3 has 6 subgroups. If you will see S4, then it will have 30 subgroups. S5 has 100 subgroups. So if n is greater than equal to m, then number of m cycles in Sn is given by n into n minus 1, n minus 2, so on till n minus m plus 1 upon m. Next, number of distinct R cycle in Sn. This is NPR upon R. 1 upon R, n factorial upon n minus R factorial. For example, number of 3 cycle in S5. So this will be 1 upon 3, 5 factorial upon 2 factorial. 5 into 4 into 3 into 2 upon 3 into 2. So 20. And if I ask you to find in S6, find how many elements of order 6 are there. So 6 order in S6 can be possible as 6 cycle, 3 cycle, 2 cycle into 1 cycle. So this will be 6 factorial upon 6 into 0 factorial. Here I have used this formula, number of distinct R cycle in Sn. And here I am using this formula which I have taught you, this one. So 6 factorial upon 3 to the power 1 into 2 to the power 1 into 1 to the power 1. So this will be 120 plus this will be 120 only. So total 240. Next, group homomorphisms and isomorphisms. Group homomorphism. Let G and G bar be two groups a map phi mapping from G to G bar is a group homomorphism if it preserves the group operation. That is phi A into B. This is equal to phi A star phi B for all A comma B belongs to G. So this is group G, this is group G bar. So I have elements A, B and AB. So under this phi mapping, A will be mapped to phi A, B will be mapped to phi B, and this AB will be mapped to phi AB, and phi AB is equals to phi A star phi B. Next, isomorphism. So isomorphism is also a group homomorphism plus 1 1 and all 2 also. So a bijective group homomorphism is called an isomorphism. If G and G bar are two groups, then phi mapping from G to G bar is an isomorphism if first one phi is 1 1, second phi is onto, third phi AB is equals to phi A star phi B for all A comma B belongs to G. The groups G and G bar are isomorphic, which is denoted by G isomorphic to G bar. Next, kernel of a homomorphism. Let phi mapping from G to G bar be a group homomorphism the kernel of the homomorphism phi is the set kernel phi. I will pick an element from domain such that it is mapped to the identity of codomain. I am denoting it by E bar. Remarks. The kernel of an isomorphism is the identity element. Let us see why is it so. If phi mapping from G to G bar is an isomorphism, kernel phi is equals to x belongs to G such that phi x is equals to E bar. If E belongs to kernel phi as phi E is equals to E bar, if I suppose that x belongs to kernel phi, this means phi x is equals to E bar. Now as phi is 1 1, because phi is an isomorphism and phi E is equals to phi x, so x is equals to E. So that's why kernel of an isomorphism is the identity element, because I have picked x from this kernel phi. Now some properties of an element under homomorphism. Let phi mapping from G to G bar be a group homomorphism and G belongs to G, then identity is mapped to identity. E belongs to G is the identity of G and E bar belongs to G bar is the identity of G bar, then phi E is equals to E bar. Second, phi G to the power n. This is phi G whole to the power n. Third, if order of G is n, then order of phi G will divide order of G. Fourth, if phi G is equals to G dash, then phi inverse G dash is equals to x belongs to G such that phi x is equals to G dash, and this is equal to G into kernel phi. Next, some properties of an element under isomorphism. Phi is a mapping from G to G dash, G bar, be an isomorphism, and G is a element from domain G. Then identity is mapped to identity. Phi E is equals to E bar. Second, phi G to the power n is equals to phi G whole to the power n. Third, if order of G is equals to n, then order of phi G is equals to n, that is order of A is equals to order of phi A for all A belongs to G. Fourth, AB is equals to BA if and only if phi A phi B is equals to phi B phi A. Next, properties of subgroup under homomorphisms. Let phi mapping from G to G bar be a group homomorphism and H be a subgroup of G, then first phi H, this is equal to phi H such that H belongs to H is a subgroup of G bar. That is phi H is a subgroup of G bar. Second, if H is cyclic, Means if subgroup is cyclic, then phi h is also cyclic. Third, if H is abelian, then phi H is also abelian. Fourth, if H is a normal subgroup of G, then phi H is also a normal subgroup of G bar. If order of H is n, then order of phi H divides order of H. If K bar is a subgroup of G bar, then phi inverse K bar is a subgroup of G. If K bar is a normal subgroup of G bar, then phi inverse K bar is a normal subgroup of G. Next, properties of isomorphic groups. These are important. If phi mapping from G to G bar is an isomorphism, then first, G is abelian if and only if G bar is abelian. Second, G is cyclic if and only if G bar is cyclic. Phi inverse G bar to G is an isomorphism. Now let us discuss some examples of homomorphisms. First, for n belongs to Z plus, the map phi Z to Zn defined as phi A is equals to A mod n for all A belongs to Z is a homomorphism. Now what will be the kernel phi? Kernel phi will be, I will pick an element from domain x belongs to Z such that phi x is mapped to the identity of codomain. Identity of Zn will be 0. Such that phi x, it will be x mod n by the definition of phi. This is equal to 0. This means generator n, the multiples of n. Second, phi is a mapping from general linear group which contains matrices of order 2 whose entries are real numbers to R star, which is defined by phi A is equals to determinant of A for all A belongs to GL 2, R. Then phi is a homomorphism. Kernel phi A belongs to GL 2, R such that determinant of A is equals to, means phi A is equals to identity of codomain. This is R star. This is group with respect to multiplication operation. So identity will be 1. Determinant of A is 1. Can you tell me what will be the kernel?
Identity matrix.
नहीं. स्पेशल लीनियर ग्रुप पढ़ा था ना, SL2R.
हाँ,
उसमें डिटर्मिनेंट ऑफ A 1 था ना.
1 था. हाँ,
आइडेंटिटी तो आपने एक स्पेसिफिक बोल दिया ना, हमें तो पूरा का पूरा देखना है. तो SL2R.
ठीक.
Third, phi is a mapping from M2, R to R, which is defined as phi A is equals to trace of A for all A belongs to 2 cross 2 real matrices. Then phi is a homomorphism. Kernel phi is equals to A belongs to M 2, R such that phi A is equals to identity of codomain, which is 0. A belongs to M 2, R such that trace of A is equals to 0. So this will be set of all matrices of 2, R, M2, R with trace 0. Fourth, phi is a mapping from R star to Z2, which is defined as Z2 contains only 2 elements 0 and 1. So phi n is equals to, and this R star does not contain 0. Only non-zero real numbers are there. So I am mapping negative real numbers to 1 and positive real numbers to 0. Then phi is a homomorphism. Now kernel phi, this is equal to n belongs to R star such that phi n is equals to 0. So 0 पे map हो रहा है means set of all positive real numbers. So this will be R plus star, means all the non-zero positive real numbers. Next, phi is a mapping from dihedral group to 1, -1, which is defined as phi alpha. We know that dihedral group consists of rotations and reflections. So when alpha is a rotation, I am mapping it to 1, and when alpha is a reflection, it will map to -1. Then phi is a homomorphism. Kernel phi is equals to alpha belongs to Dn such that phi alpha is equals to identity of codomain, which will be 1. So set of rotations, because when alpha is a rotation, it is taking the value 1. So generator R, where R is the rotation by (360/n degree). Sixth, phi is a mapping from Sn to 1, -1. Phi sigma is equals to, and we know that Sn consists of even and odd permutations. So when sigma is an even permutation, I am mapping it to 1, and when sigma is an odd permutation, I am mapping it to -1. So phi is a homomorphism. Kernel phi, this will be sigma belongs to Sn such that phi sigma is equals to identity of codomain, which is 1. So set of all even permutations, and set of all even permutations is alternating group An. Next, let G is equals to R square, operation of vector addition. G bar is equals to real numbers. Phi is a mapping from R square to R, which is defined by phi x comma y is equals to x. Then phi is a homomorphism. Kernel phi, this is equal to x comma y belongs to R square, such that phi xy is equals to identity of codomain, which is 0. And by definition of phi mapping, it is x. So x is equals to 0. 0 comma y belongs to R square. This means it is y axis. Next, phi is a mapping from z direct sum z to z, which is defined as phi a comma b, this is equal to a minus b. So phi is a homomorphism. Kernel phi is equals to a comma b belongs to z direct sum z, such that phi a comma b is equals to identity of codomain, which is 0. A minus b is equals to 0. This will be ordered pair a comma a, such that a belongs to z. Next, some results on homomorphisms. First, let phi mapping from G to G bar be a homomorphism, then kernel phi is a normal subgroup of G. Next, number of homomorphisms from Zn to Zm This is GCD of n comma m. This is important. Third, number of homomorphisms from Zm direct sum Zn to Zl. This is GCD of m comma l into GCD of n comma l. Number of homomorphisms from Zn to Zm cross Zl. This is GCD of n comma m into GCD of n comma l. The number of group homomorphisms from Z10 to Z20 is A part 0, 1, 5, 10.
Ten.
Yes, simply GCD of 10 and 20.